Airplane tickets are unpredictable and can range anywhere between 50 to 300 Canadian dollars. We were inspired by the idea of demystifying airfare pricing. We believe consumers deserve to know whether they've got a good price for the ticket and what drives the cost of plane rides to be sky high. Two similar flights can have drastically different prices, and consumers often have no way of knowing whether a fare is reasonable or inflated. And so, can we predict the baseline flight prices and identify overpriced flights? Can we determine the main factors that affect the increasing flight costs? And what are the best alternative destinations that can maximize our cost effectiveness? From this graph, we can see the average prices of a large portion of flights are significantly more expensive than the cheapest available options.
Predict price per mile, since from this graph, ticket prices are pretty heavily correlated with flight distance, so the price per mile is a good indication of cost efficiency. And then here is the distribution of the price per mile data. To predict the price per mile, some data we used includes distance, number of passengers on the route, the time period, as well as some constructed parameters such as hub intensity and the carrier large and low frequencies.
We trained a gradient-boosted decision tree with XGBoost to predict fare per mile for flights. Then we computed SHAP values to determine which factors influence the predicted fares. We flagged flights as inflated if actual fare was greater than predicted fare by 15%, and suggested alternative destinations with lower cost per mile.
So here we have the map of the United States, which represents the inflation of different prices of flights, where each line represents a flight, and the more red a line is, the more inflated it is. This was made using PyDeck. Then we see another map, which has two flights on it. This one is from Tampa, Florida, going all the way to Los Angeles, and this color represents that it is extremely inflated. And so a suggested alternative destination would be instead to go to Alabama.
Here is the result of the SHAP analysis. Looking specifically at NKM, which is the flight distance, these blue points, which represent short flights, have very positive SHAP values, while the red points, representing long flights, have negative SHAP values. This suggests that the shorter flight distances increases the baseline cost per mile, while the longer flights have lower costs per mile. We can come to similar conclusions about these next few features, although they seem to have less effect compared to distance, since their SHAP value magnitude is a bit lower. And lastly, these ones at the bottom, they look pretty much like lines, so this suggests that they do not affect the model that much. And then here are some visualizations of the correlation between cost per mile and each factor from the SHAP analysis, which we consider to be somewhat influential.
So here we have a short demo on Power BI where we see we have a pie graph that shows the carriers of inflated flights ordered by the year. And so in 2024, the carrier DL gave 24 inflated flights, which was approximately 36% of all the inflated flights in 2024. And then notice that in 2023, DL also gave the most number of inflated flights out of all the carriers. And we can use the splicer here to look at the different years and which carriers gave how many inflated flights. Next, we also can look at the right and notice that we have a line chart that shows the average price of plane tickets per quarter over 4 quarters. And notice that quarter 3, the cost of the plane tickets is generally the lowest.
FlightID is a diagnostic engine designed to cut through the complexity of aviation pricing. We move beyond the typical black box approach to price prediction, delivering a model that is both highly accurate and fully interpretable. At the core, we implemented an XGBoost gradient-boosted machine regressor. By utilizing a sequence of optimized decision trees, our model identifies complex nonlinear patterns in fare dynamics that traditional linear models fundamentally miss. Our model is highly responsible and transparent. By integrating Shapley additive explanations, or SHAP, we decompose every fare prediction into its contributing factors based on game theory. Our analysis proves that distance and passenger volume are the true drivers of fare structure. Crucially, our model's ability to correctly identify noise, like hub intensity, as insignificant, is proof that it is learning generalized market logic rather than overfitting to specific data anomalies. We didn't just chase low error numbers. We validated our performance through rigorous benchmarking. We achieved a mean absolute error of roughly 0.018, which significantly outperformed our linear regression baseline. Our residual distribution shows a near-normal symmetric bell curve centered at 0. This symmetric distribution serves as our formal proof against overfitting. It demonstrates that our model is statistically unbiased and generalizes reliably across the entire US aviation market.
Our SHAP analysis proves that the flight distance is the overwhelming primary driver of fare structure, acting as the baseline control for all our predictions. Then beyond distance, we identified that the number of passengers per route and the frequency of large carriers are also pretty influential factors, suggesting that our model is learning how volume and airline dominance influence pricing. Additionally, the time and quarter are also influenced baseline prices. Interestingly, though, our model found that spatial metrics such as hub intensity have negligible impact on fare inefficiency, suggesting that these factors don't really drive price gauging.
FlightID transforms raw flight data into a spatial diagnostic tool for market efficiency. We aren't just predicting prices, we're identifying where the market is failing the consumer. FlightID allows regulators to identify fare inflated routes where market concentration, rather than operational costs, is driving prices up. For carriers, this tool identifies gaps in competition where current service is inadequate or overpriced, pinpointing ripe opportunities for new market entry. By identifying alternative gateways, FlightID provides actionable insights that help travelers and corporate travel managers optimize their routing. Unlike manual audits, this model scales across the entire national aviation network, instantly flagging anomalies across thousands of routes. Because we utilize SHAP-based interpretability, we explain the why. Our model's near-normal residual distribution proves it is a robust, generalized tool, not a black box algorithm that overfits to noise.